Okay, so what we have is a rolling body given to us. We know the radius, we know the mass, and we know the moment of inertia about its center of the mass. So on taking the components of the forces, what we find, we are going to have normal component mg cos theta, mg sin theta, and we need to decide which way the friction force will act in case if it is going to act. So since it is going to be accelerated rolling on a stationary surface, so what is the condition we have got is ACM must be equal to R alpha. Now, next I'll ask you, you check out the torque that is going to be acting on our object about the center of the mass. So what all forces I have got is mg, which is going to be having no torque about the center of the mass. The normal contact force also passing through the center of the mass, the torque of the normal contact force about the center of the mass 0. And because of the mg sine theta down the inclined plane, we are going to see center of the mass's acceleration, which is going to come in the direction down the inclined plane. Correct. Now, what we have got is we have got something present to provide us ACM. So I've got mg sine theta acting down the inclined plane, which is going to bring ACM. But I don't have anything to give us alpha, no? Correct, because alpha is going to be present, going to be there only when there is going to be some torque about the center of the mass. So torque of the normal contact force 0, torque of the gravity 0. So there is no torque because of these forces about the center of the mass. So how come I'm going to have any alpha about the center of the mass? It means there must be some force which must be causing some torque about the center of the mass so as to get an alpha about the center of the mass. No? But I want that point of contact to be not slipping so what all accelerations it is going to have, it will be having ACM down the inclined plane because of the translational motion of the center of the mass. And the other acceleration R alpha that it must be getting should be up the inclined plane. Now tell me, in order to get this R alpha present up the inclined plane, what must be the sense of alpha we need to have about the center of the mass? Can you tell me? R alpha is acting up the inclined plane, so the sense of the alpha should be this sense. No, what is that sense? Is anti-clockwise. So it means I need alpha to come anti-clockwise. So it means the torque about the center of the mass must be anti-clockwise. Net torque about the center of the mass must be anti-clockwise. And what we find, torque of the normal contact force 0, torque of the gravity 0 about center of the mass. So it means only one force left, which is friction force, about which we have not thought of what it will do. So it is only friction force that is going to have some torque about the center of the mass, and we want net torque to be anti-clockwise. That is only possible if the friction force is going to act up the inclined plane or not. I hope all of you are understanding this point. How I am deciding which way the friction force will act. I'll give you a minute to digest that, whatever I've told. Pavisya, you came now, just I'll repeat for you. So we've got a rolling object on an inclined plane having mass m, radius r, moment of inertia about the center of the mass given. And if I draw the free body diagram, what we find mg sine theta, mg cos theta are the components normal contact force will act. And we need to know in case if friction force acts or not. And in case if it acts, in which direction it will act, whether down the inclined plane or up the inclined plane. Since it is rolling without slipping, so what kind of friction force is going to be present? First of all, it will be static friction. So we don't know the magnitude. And only thing we know that whatever the friction force will be, either it may act up the inclined plane or it may act down the inclined plane. Okay, you got disconnected again, no? So anyone can tell the ACM is going to be down the inclined plane. And in order to have the point of contact to be having 0 acceleration, the R alpha must come up the inclined plane to cancel out ACM. So for R alpha to come up the inclined plane, we need alpha about the center of the mass to be anti-clockwise, correct? And to have alpha anti-clockwise, the net torque about the center of the mass must be anti-clockwise. And next, if you see who all can apply torque about the center of the mass, so normal contact force will not be having any torque, mg will not be having any torque. So friction force only left to talk about. The friction force must be giving me this anti-clockwise torque. So to have anti-clockwise torque, the friction force must be acting up the inclined plane. I hope all of you understood the logic behind how I came to the conclusion for the friction force to be acting up the inclined plane. I wish I understood now. You got disconnected again. Understood or not? You can reply through text also. All of you understood this point or not?
Yes, sir. Understood, sir.
Okay, then. So after that, what we do is same old thing. We'll write down the things for the translational motion of the center of the mass. So what we have got is the center of the mass is going to be having acceleration down the inclined plane. So we will consider finding out net external forces acting down the inclined plane. So net external force acting down the inclined plane, I can write it down as MACM. And what is the net external force we have got? Mg sine theta acting down, friction force acting up the inclined plane. So net force acting down the inclined plane will be mg sine theta minus MACM. So this is going to be our equation number 1. After that, we must write down the torque equation for the net torque acting about the center of the mass. So only force that is going to cause torque about the center of the mass is the friction force, and it is acting tangentially. So what will be the lever arm of this force that anyone can tell? It's going to be the radius itself only, no? So the lever arm of this friction force is our capital R. So net torque about the center of the mass, we write it down as ICM into alpha. So what we have is net torque, only torque is going to be because of the friction force. So FR will be equal to ICM into alpha. This will be our equation number 2. And then finally, we'll be using this equation ACM equals to R alpha, the rolling constraint, in this case, equation number 3. Using these 3 equations, we can solve for. So what you do, you figure out what will be the friction force, what will be the ACM. Everyone do that now. I have given you 3 equations, 3 unknown. Please solve for friction force and ACM. So Sudarshan, you've joined now. Okay. Just I'll repeat it as fast as possible. So we've got a rolling body whose mass, moment of inertia, radius known. And we have to figure out what will be the friction force acting on it if it rolls down the inclined plane and the acceleration of the center of the mass. So the friction force must be acting up the inclined plane. We came to the conclusion from the fact that since ACM will be down the inclined plane, to have acceleration of the point of contact to be 0, R alpha must come up the inclined plane. For that to happen, alpha must be anti-clockwise. And for alpha to be anti-clockwise, torque about the center of the mass must be anti-clockwise. Tired of repeating this thing, still I repeat. And then if you will see, torque of the normal contact force 0, torque of mg 0, it means some force must be present whose torque should be clockwise, anti-clockwise. So it must be the friction force which must be bringing anti-clockwise torque. So for that to happen, friction force must act up the inclined plane. It has got 2 choices only, either it can act down or it can act up the inclined plane. So to have friction force to be giving us anti-clockwise torque, it must act up the inclined plane. And it should be static in nature. Then we write down the force equation, torque equation, and then the constraint equation. Then we solve for the unknown, which is friction force and ACM. All of you do that and tell me what answer comes. I'll not do the calculation. Even It's very simple. You consider using the value of the alpha in terms of ACM in equation number 2. So what we get is FR equals to ICM into alpha, which is ACM by R. So F will be equal to ICM ACM by R square. Okay. Then I will use this value of the friction forces in equation number 1. We'll be having mg sine theta minus ICM ACM by R square, which is going to be equal to MACM. Then you solve for ACM, it is going to come equal to mg sine theta by m plus ICM by R square. And so what I'll do, I'll consider writing it down in some different fashion. So I hope I can take a new page now. I'm going to share this thing, so no need to take. You can copy it afterwards, or you try copying it as fast as possible. I don't trust that you will be copying it afterwards. So even though I've got scarcity of time, still I'm giving you time to copy. So copy fast, everyone. I have told no radius of gyration. I have talked about it or not. Tell me, anyone. Who is there or not? Aswin, radius of gyration we have taken in class. Rupesh, Amir Khan. Radius of
No,
gyration.
sir, we didn't take that, sir.
Okay, a simple thing only. So copy this thing. Maybe I'll talk about that. After copying, let me know. Okay, I can take a new page now. Okay, I can take a new page. Think I've given enough time. Not copied, you tell me. What is radius of gyration? It's a very simple thing. Suppose if moment of inertia about some axis is given to us as I. So what we do, we equate the moment of inertia to mk square, where m is the mass of the system and the k is the thing which is called as radius of gyration. For example, if I am giving you a disk Suppose if I'll give you a disk of mass m and radius r, and if I'll ask you what is the radius of gyration we have got about the axis of the disk. So the moment of inertia about the axis of the disk is mr square by 2. So we will equate it to mk square. So what you get, gone, so k will be equal to r by root 2. So this will be the radius of gyration of the disk about its center of the mass axis perpendicular to the plane of the disk. Understood? So in case if I have a ring, suppose instead of a disk, same axis if I consider, if I give you a ring, the moment of inertia of the ring about that axis, about its own axis is going to be mr square. So we'll equate the moment of inertia, which is mr square, to mk square. So the radius of gyration is going to be r. So this is something which is called radius of gyration. Sometimes we write the moment of inertia in terms of radius of gyration also. So what we have got in this example as ACM came out to be equal to mg sine theta divided by m plus ICM by r square. No? So what I will do, I'll write down ICM as mk square and I'll take out common m from the numerator and denominator. This expression will become ACM will be equal to g sine theta by 1 plus k square by r square, correct? Now tell me, once I'm going to write it down in terms of in this way, what you see is the acceleration of the center of the mass is independent of the mass, no? See, as long as I give you a disk of radius r, the radius of gyration is going to be r by root 2, doesn't matter what may be the mass of the disk, correct? No? So whatever I have k square is the radius of k, here is the radius of gyration. It is not something which depends upon the mass, it depends upon the mass distribution, correct? So this ACM, the acceleration of the center of the mass, you see, it is something which is independent of the mass of the system, no? Correct. Now next we will find friction force. So what we have got friction force as ICM ACM by R square. The friction force we got it to be equal to ICM ACM by R square. So I'll write it down as MK square. So it's going to be MK square by R square into ACM. Just I'll multiply ACM. We are going to get mg sine theta. Just simplifying it, I'll write down as 1 plus R square by K square. Correct? Check once. Correct only, no? So what we get is friction force is going to be equal to mg sine theta by, you are supposed to remember this two results, okay? Not only you need to know how to solve for it, even you need to remember the results. The friction force is going to be equal to mg sine theta by 1 plus r square by k square. So what is this friction force is? It is the friction force that we need to act for this thing to be able to roll without slipping, no? But there's a limit up to which friction force can give us some force, no? So the maximum the friction force can become is mu times normal contact force, which is mg cos theta in this case, no? And what we have got is the demand I have from the friction is to give us mg sine theta by 1 plus r square by k square. So for friction force to be able to provide this much, we must be having this thing or not. The demand from the friction force is F. Only when it is possible for it to be able to supply that, when it is lesser than whatever maximum it can supply, correct? So the F must be less than or at least equal to the maximum friction force, which will be mu times. So what we get is mg sine theta by 1 plus k square by r square must be less than or equal to mu times mg cos theta. What we have is mu must be more than or equal to tan theta divided by 1 plus, just a moment, it's r square by k square. 1 plus r square by k square. So the minimum possible value of the mu should be is tan theta by 1 plus r square by k square. Even you're supposed to remember this result. May come handy, remember it. And you should not forget the fact that even this mu minimum, is it not independent of the mass? Because in future, I'm going to give you a question where you must be knowing this concept that ACM is independent of the mass, whatever is the mass of the body. And also, one more thing is there in that question. So please don't forget that result and also the significance here. Understood now, everyone? Copy this thing. After copying, let me know. Okay, I can take a new page now. All of you understood?
Sir, yes, sir, you can take new page, sir.
Okay, then. Next, we are going to talk about angular impulse. Okay. Like the way in our center of the mass chapter, we were writing down no impulse, linear impulse. That was nothing but the change in the linear momentum. Same way, it is going to be the change in the angular momentum. So what we can do, I can write down net torque to be equal to rate of change of angular momentum. This is the net torque is going to be equal to rate of change of angular momentum. So dl I can write down as tau dt. And then on integrating both the sides, just like the way we did earlier, suppose from time interval t1 to t2, and when the momentum was suppose L1 and L2, so this side then integrating will be getting L2 minus L1, that I will write it down as delta L, and this will be integral of tau dt. So this thing is some which is nothing but change in the angular momentum. And the symbol that we use, that I will use, is suppose J theta. Then this is some which is called as angular impulse. Just like the way the impulse is the change in the linear momentum, same way the angular impulse is the change in the angular momentum. So in case if you are given the plot between the net torque and time, the area under the plot is going to give you the change in the angular momentum. So if I'm going to give you the net torque versus the plot, the area under the plot is something which is the change in the angular momentum or angular impulse. Okay. Now, there we had impulsive forces, no? So what all forces were called as impulsive forces? It was some force which is supposed to be of very large magnitude, and generally they act for very small time. Even in that small time, they were able to change the momentum of the object or the system by finite amount, correct? Same way here, what kind of torque will be called as impulsive torque? The one that can bring finite change in the angular momentum, even it acts for a very small time interval. So if I have a force which is impulsive in nature, and if it is acted at some distance r, which is such that R cross F is not non-zero. In case if it has got some torque about some axis, since the force is very big, so the torque it is going to bring will be also very big. So the torque of the impulsive forces, in case if there is some torque present, will be impulsive in nature, no? Correct. The torque of the impulsive forces is going to be impulsive in nature. Okay. Take a new page. I'll take an example in the next page. Copy this thing fast. Haris, you tell me after copying. Okay, you can take a new page, no? Okay.
Yes, sir.
So if I'll give you a question, there's a rod which is hanging in the vertical plane about one of its ends. Suppose it is hinged at the point O, and then we are applying a impulse or an impulsive force at some distance x from the point of suspension. Okay, so what we have got here is a uniform rod of mass m and length L suspended in vertical plane about the point O, and we are applying an impulse or an impulsive force perpendicular to the rod at a distance x below the point of suspension. And we are supposed to determine the angular velocity this rod will get just after the application of the impulse. So what we have is, like the way in the case of events of very small time interval like collision, what we were doing, we were neglecting the non-impulsive forces. No? Same way, what we are going to do in the cases of when we have things like collision or impulsive action, the the torque of the non-impulsive forces will be neglected, correct? So here, if I consider the torque of the gravity is zero at this position of the rod, no? So even though it is zero, even if it was non-zero, but still we are going to neglect the torque of non-impulsive forces in case if we have got events of very small time interval and we have got presence of the forces which are impulsive in nature, bringing impulsive torque. So what I'll write that point even. So torque of non-impulsive forces are neglected. And how we are going to apply an impulse? Maybe we are going to hit it with some moving ball. Maybe we are going to punch it here. Whatever way, we are going to hammer it here. So whatever we did here is something which is going to be applying a force, but that force is very large and it is going to be applied for very small time interval. Now, one thing is sure that just after this force is being applied, this rod will end up moving in this sense. No? Suppose just after the impulse, the rod rotates with omega. And the force that is going to bring that the impulse, whatever is coming, is suppose is because of the force F. Okay. So what we can do, suppose if I'll find the torque of this force about the point of suspension O, so the lever arm of this force is x only. So torque of this force will be F into x. Correct. And the impulse of this force is J. So what basically it means, J will be equal to integral of F dt. So the angular impulse of this force, what we will be writing it down as integral of tau dt. As you can see, the only thing that is having torque about the point of suspension is this force. Because gravity's torque, even though it is there, it is going to be neglected. We don't have to worry about that. Normal contact force or hinge reaction, even if it was big, we don't have to worry about it because the torque of those forces which are acting at the point O will be zero. So torque of the hinge reaction will be zero, even though it may be impulsive in nature. So we don't have to worry about that. And gravity's torque, even it is there, even it is present, we don't have to worry about it since it is non-impulsive. So only thing that has got torque about point O is this force F, whose impulse is J. So the angular impulse, what we write down? Net torque, integral of net torque into dt. So what is our net torque? It is going to be F into X. So I can take out X or not, because during the time when we are applying this force F, the rod will not be getting displaced at all, correct? Do you remember that point or not? During the collision, the position of the objects just before and just at the end of the collision is going to be same only or not? Because even though they are subjected to very large accelerations, but the those accelerations are going to last for very small time interval. So the displacements of the object during such kind of small time interval events will be neglected, no? So it means just during the application of this force, that time interval I'm talking about, the position of the rod will not be changing at all. So the point of application of this force will be at same perpendicular distance, correct? No? Or the line of action of this force will be at same perpendicular distance for the time duration for which it acts on the rod. So this x is something which is going to be a constant, so can be taken out of the integral. So we'll be getting x into integral of f dt. And what exactly is the integral of f dt? Is it not the impulse of that force? So the angular impulse is going to be equal to x times j. I hope all of you understood this thing. Got it now? And what we are doing is we are considering torque about O. So torque of the hinge reactions, even if it was impulsive, is going to be zero because they are acting at the point of rotation only. And the torque of mg zero. But even if it was not zero, torque of mg is going to be neglected. So the only force that is having any torque about the point O is the force that is the impulsive force of that acts, whose impulse is given to us as J. So the torque of that force, we can figure out, it's simple only, F into X. So impulse of that force is given to us, which is integral of F dt. So the angular impulse I can write down as integral of the torque dt. Torque is F into X, plugging it in there, X can be taken out of the integral. And then we can write instead of integral F dt as J. So the angular impulse is going to be X times J. All of you understood this point or not? All of you understood, no?
Yes, sir.
Okay. So after that is very simple. Suppose if I would have given you a question like there's a block kept on a surface, maybe smooth surface, and we apply an impulse J, and mass of this block is m. Just before the impulse, it was moving with zero momentum. And we assume that after the impulse, it will end up moving in the rightward direction with velocity mv. So it will be having final momentum mv. Then what we have is only one impulse acting on the object. What we did there was we considered the direction of the impulse to be taken as positive. Now, what we have is only one force is causing a torque which is impulsive in nature. So there's only one impulsive torque, which is the torque of this force. I'll try to relate this thing. See, here I have only one impulse, the impulse of this force, just one impulse. No? So we took the direction of the impulse as positive. And here we have got torque acting because of only one force F. So we have got the angular impulse only because of the torque of this force. So whatever is the direction of the torque or whatever is direction of the impulsive torque, like the way whatever is direction of the impulsive force, same is considered as the positive direction. So what is the sense of the torque that is going to come because of this force F? So torque of this force about the point O, what is the sense of this torque is anti-clockwise as seen from your side or not? Anti-clockwise, no? What is the torque direction is anti-clockwise? Sense I'm telling, anti-clockwise. So what I will do, I'll take anti-clockwise as positive. just before the impulse was applied, it was not rotating at all. So just before the impulse, the angular momentum about this point was zero. So initial angular momentum about the point of rotation is zero. And what kind of motion it is? Pure rotational motion. So what will be the final angular momentum is going to be moment of inertia I about that point into omega. And what is the sense of it is going to have will be anti-clockwise. So what we write down, the angular impulse is going to be equal to change in angular momentum. And we have taken anti-clockwise as positive. So what we have is final angular momentum plus I omega, since anti-clockwise taken as positive, initial angular momentum 0, and the angular impulse is x times j. So what we get, omega is going to be x times j by I. And you can plug the value of the I, which is going to be ml square by 3. So it's going to be 3xj by ml square. All of you understood this thing or not? Easy only or not? Like the way there we had one force, so we took the direction of the force as positive one. Here I have got only one torque, so we took the direction of the torque as positive one. I hope I'm clear. All of you got this thing. Okay, copy this thing everyone. After copying, tell me. Copy this one everyone. After copying, tell me. Okay, I can take a new page.
Yes, sir.
So now here what we had was rod was hinged in the vertical plane. So things were simpler for us because all the motion was simple only. It will undergo pure rotational motion about the hinge point. But suppose instead of the rod being hinged, it is kept on a smooth horizontal surface. Suppose what we have is the rod is kept on a smooth horizontal surface, and an impulse J is applied as shown. Determine the VCM and omega of the rod just after the impulse. Now, what kind of thing it is? Suppose if I have kept the rod like that and then I'm going to hit it somewhere here. Suppose if it is given that we are going to apply an impulse at one of the end of this rod. So tell me, can you guess what kind of motion this rod will have? So what exactly we did here applying an impulse? We are applying a force which is going to last for very small time, but that force is going to be of very large magnitude such that it can cause finite change in the momentum, even though it acts for very small time. Like you can keep a pencil on the table and then you strike it somewhere at one of the ends. I am asking you, what kind of motion the center of the mass must be having just after the impulse? So I'm applying a impulse, just you should not be getting confused about it. You think of as if I am applying a force only, just the difference is the force is of very large magnitude and will be acting for very small time. So in such kind of events, I told you that the object's displacement will be considered negligible because even though the object is experiencing a large acceleration, suppose if I'll use that s equals to ut plus half at square also. So what we have is the object is starting from rest, so u0. And then what we have is the displacement will be roughly, I can say, even if I consider the acceleration constant and very, very large. So acceleration very large, but I'm multiplying it with the something which is t square, where t is very small. So t square is going to be very, very small, such that on multiplying this almost nearly zero or something which is almost zero to something very large is going to give us something which is going to be nearly equal to zero, but whatever it must be should be very small. So the displacement of the objects during the events of a small time interval like collision applying some impulse will be considered very, very small or neglected. So because of that, the position of the rod just before the impulse and just after the impulse will be same only. Correct. So tell me, this rod must rotate or not? Tell me, the rod must rotate or not? Because we are applying some force which is not acting at the center of the mass. So this rod may rotate. So if this rod is going to rotate, about which point it should rotate? Can you tell me? You will tell me center of the mass, obviously. So why the rod should rotate about the center of the mass just after the impulse? So to understand that, what I will do, suppose if the rod is going to rotate, not about the center of the mass, suppose some another point, maybe the topmost point. So just after the impulse, whatever the kind of motion the center of the mass will be having will not be a straight line motion. It will be moving along some curved path. Right? If center of the mass moves along the curved path, then the acceleration of the center of the mass will be non-zero. But since for the time for which we are applying some external force, till that time only the center of the mass must undergo acceleration, correct? Once the force application is over, once there is no external forces acting on the system, then the center of the mass must not be having any acceleration. Because we see what we did here is we are applying a force which is going to last for a very small time. So during the time I was applying the force on it, till that time the center of the mass must be accelerating, okay. But once I have removed that force application, once that force application is over, then the center of the mass must not be having any acceleration and should be moving with constant velocity. But since we are applying some force which must cause rotation, so only way possible is to send possible it is only way it is possible for the center of the mass to continue moving in a straight line just after the impulse if the rod rotates about the center of the mass only or not. I hope you're understanding that point, why the rod must rotate about the center of the mass. This is an unhinged rod placed on a smooth horizontal surface. This small point, all of you are getting it or not? That just after applying an impulse, this rod, in case if it rotates, must be rotating about the center of the mass. Vidubala, you got disconnected. You understood this point or not? Rupesh understood, no? Okay then. So I'll write that point. Just after the impulse, And since we have applied an impulse, because of that, the center of the mass must be having some change in velocity, because on applying an impulse, the momentum of the system will change, and changing momentum of the system means what? Changing the velocity of the center of the mass only or not. So what we will do here, first we'll write down like the way we were writing down two things earlier, writing down the force equation for the center of the mass's acceleration and the torque about the center of the mass. Similar thing we'll be doing here. So first we'll be writing down linear momentum equations, impulse and linear momentum equations like the way we wrote down in earlier chapter for the center of the mass's translational motion. And then then we'll be writing down the torque angular momentum equation for the rotation about the center of the mass. So first we will consider the translational motion of the center of the mass. So what we write down, net impulse is going to be equal to change in the linear momentum. So just before the impulse, the VCM is 0, and just after the impulse, the center of the mass is going to be moving with MVCM. So what if you do? If you think as if I'm talking about a point mass on which we are applying an impulse J, and the mass of this point mass is same as the mass of the system M. Just before the impulse, initial momentum of this point mass 0. After the impulse, this point mass moves with VCM, so the final momentum it will be having is MVCM. So we'll consider some sign conventions, so only one impulse acting on our object. So we will take that direction as positive. So what we have is J will be equal to final, which is plus MVCM initial 0. So J will be equal to MVCM equation number 1. So velocity of the center of the mass is going to be equal to J by M just after the impulse. So what we are considering here is just after the impulse, the center of the mass will be having some velocity and the rod will be having some omega about the center of the mass. And by the way the force acts, you can tell the kind of torque it will be bringing about the center of the mass will be anti-clockwise. So the omega it is going to get will be anti-clockwise. So we need to find VCM and the omega the rod gets just after the impulse. So I'll take a new page and there I will find the omega. I hope all of you understood now. Finding out VCM very easy, just have to write the things for the linear momentum, and linear momentum finding out is same as finding out the momentum of the center of the mass. Correct? No? Linear momentum of the system is same as the momentum of the center of the mass. What it is? MVCM, no? So see, to check out what is the change in the linear momentum, just we have to see the change in the center of the mass's momentum. Okay, I'll take a new page. So what we have is we are applying an impulse J at one end of the rod. Suppose the force which causes this impulse is force F. So what we must be writing down Js, J will be integral of F dt for whatever time this force will be acting on this rod. Then what I'll do is I'll find out what will be the net torque I'm going to have about the center of the mass. So only thing that is going to have any torque about the center of the mass is this force, and it is acting at a perpendicular distance of its line of action, which is L by 2 from the center of the rod. So only torque I have got is because of this force, so it is going to be FL by 2. So what we write down the angular impulse as integral of tau dt, no? And what is the torque we have got here is FL by 2 dt. So L by 2 will be taken out of the integral. So what we get is integral of F dt. And what is our FDT? It is our linear impulse J. It will be JL by 2. So we have got one equation J theta equals to JL by 2, where J theta is the angular impulse. Just before the impulse, the nothing was happening. Initial angular momentum about the center of the mass 0. And just after the impulse, it rotates with omega. So final angular momentum is going to be ICM omega. And in what direction it rotates? In anti-clockwise sense, no? And the torque of this force is also going to be in anti-clockwise sense. So only one torque which is impulsive and its direction or sense is anti-clockwise. So what I'll do, I'll take the anti-clockwise as positive. So what we have is initial angular momentum 0, final angular momentum plus ICM omega. So what we can do, we can write down J theta to be equal to change in angular momentum. J theta is JL by 2. Initial is 0, final is ICM omega. So it's going to be ICM omega. So omega will be JL by 2 ICM. And what is our ICM? ML square by 12. So it's going to become 6 JL by M. So this is going to be the angular velocity it will be having just after the impulse. I hope all of you understood this thing. Copy this one. After copying, tell me. Just a moment. I have to open that RPD module. So angular impulse also over. So our syllabus for RPD is over, except one extra topic, that is instantaneous center of rotation. Okay. Now, okay. I'll take a new page. Just one small thing I have to tell you, which is regarding that rolling down the inclined plane only. Suppose if I give you that there's an object, maybe a cylinder or something, kept on the top of the inclined plane and released from rest. And we have to determine the angular velocity and the center of the mass's velocity once it falls through some height h. Okay. Suppose it is here and it rolls down the inclined plane and it reaches the bottom of the inclined plane. In doing so, the center of the mass of this thing falls through an height, suppose h. So, and if I ask you, suppose the height through which it falls through is suppose h, okay, the center of the mass falls through an height h, and it travels a distances down the inclined plane. So, since it is rolling without slipping, so what will be the work done by the friction force? Since whatever point, the one that comes in contact will not be slipping at all. So the point of application of the friction force is not getting displaced whenever whichever point comes in contact, not getting displaced. So work done by the friction force will be 0. Work done by the normal contact force 0 only. So only thing that is doing work here is gravity, which is a conservative force. So we can conserve the total mechanical energy. So since work done by the friction force is going to be 0, so we can conserve total mechanical energy. So just I'll write down U1 plus K1 to be equal to U2 plus K2. So if I consider the final height of the center of the mass, wherever it is, to be the reference, so what we have is initial gravitational potential energy will be mgh, starting from rest, so kinetic energy 0. And finally, wherever it is, that is taken as a reference point, so final potential energy 0. And once it reaches here, it will be moving with VCM and it is going to have some omega as well. So the kinetic energy of the combined motion, we write it down as half mvcm square plus half ICM omega square, no? And since it is rolling without slipping, so VCM will be equal to R omega. So if I want to find VCM, accordingly, I'll replace omega, I'll write down as VCM by R. So it will be half ICM into V square by R square. Further also I can solve it. I can write it down as ICM as mk square. So mk square V square by R square, which is going to be equal to mgh. So you see, mm will get cancelled from everywhere. And VCM is going to be equal to 2gh root over 2gh by 1 plus k square by R square. No, correct? Check that. Or even we can solve it by equation of motion also, since ACM is known to us, which is g sine theta by 1 plus k square by R square. No, so what I can do, I can use VCM square equals to UCM square plus 2AS or 2ACM into displacement S. And UCM 0 only, so it's going to become, so 2G sine theta into S by 1 plus K square by R square. Now, in this triangle, this angle is theta only or not? And I can write down the sine theta as H by S, correct? So replacing sine theta by H by S, it will become 2GH by 1 plus K square by R square, which is equal to PCM square. So you see, we are going to say get same answer, whether you do it by kinematics or whether you do it by energy conservation. I hope all of you understood this thing. There are some extra topics, not in this syllabus, but I want to teach those extra things also, because in understanding those things, you will be becoming good in the things that are in syllabus also. But that I'll be taking in extra class after this test. Okay. Those are at JEE Advanced or maybe more than that also. JEE Advanced over, but still I teach some extra things. That is not something you will find in regular books also. But even without, anyone can manage JEE Advanced, but with that it will make the things a little bit easier. Copy this thing, everyone. After copying, tell me. Okay, I can take a new page.
Yes, sir.
Next step, we will do one question which involves impulse as well as rolling without slipping. Suppose what we have here is a sphere, a solid sphere of mass m and radius r. And what we are going to do is we are applying an impulse at the height x from the center of the mass. Okay. So we are applying an impulse at height x from the center of the mass, and it is kept on a rough horizontal surface. So we are supposed to determine what must be the x so that it rolls without slipping just after the impulse. So maybe it is like a ball that we have got in that, what is that called? Pool game, that snookers, I think it is called. Snookers called, it's called pool game, that one. Correct. So it is like the ball that is snooker ball, and you're hitting it with the cue or that stick that is there, and we are hitting it at a height x from the center, and we are supposed to determine what must be the x so that it rolls without slipping just after the impulse. All of you understood now what kind of situation it is? So what we have is again two things we write down. One is for the translational motion of the center of the mass. Instead of net external force equals to MACM, we'll be writing down J equals to delta P. And next, for the rotational motion about the center of the mass, for that instead of net torque equals to ICM alpha, we'll be writing down net angular impulse about the center of the mass to be equal to change in the angular momentum. The first thing is so what we do, since it is going to undergo rolling without slipping just after the impulse, so I'll assume that it will be getting a velocity VCM this way just after the impulse and omega in this manner just after the impulse. So first we will be considering the translational motion of the center of the mass. For that, we'll be writing down impulse momentum equation J equals to delta P, and only one impulse acts on the system. See, you may tell sir friction force may come into picture, but tell me, in case if friction force comes, and for what time duration we are considering, things must be clear to you. The time duration for which the stick is going to be in contact with the ball. So we have got a ball kept on a surface, we are going to hit it with a stick. And then the time duration for which the stick will be applying force on our ball will be very, very small. No? So that time duration is the time duration we are talking about. So during that time duration, whatever friction force will come is going to be non-impulsive in nature. Why? For friction force to be impulsive in nature, the normal contact force must be impulsive. And in here, the normal contact force will be equal to mg because whatever impulse I'm applying is parallel to the surface. We don't have any component of it along the surface. Get that? So here friction force is going to be non-impulsive, normal contact force non-impulsive, mg non-impulsive. So we neglect them. So only force which is having impulse is the whose impulse is j. And what is the, suppose that force is F. So what we write down J will be equal to final momentum. So initial momentum of the system 0. Final momentum is MVCM, which is in rightward direction. And I'll consider that direction is positive, since that is the direction in which our impulse J is acting. And that is the only impulse that is acting. So J will be equal to MVCM. That is very easy, just like earlier one. So VCM is going to be equal to J by M. Now, whatever this impulse is, it is coming because of some force. No, suppose the force which brings this impulse is the force F. So what we do next is we find the torque of that force or the torque of the impulsive forces, whatever I have got, about the center of the mass. But the thing is that we've got only one impulsive force. So next we'll be writing down things for the rotational motion about center of the mass. So the only torque I have got which is going to be impulsive is the torque of this impulsive force F. and its line of action is at a perpendicular distance x from the center of rotation, whichever is considered here, no, the center of the mass. So here r perpendicular is x only, and the torque of this force about the center of the mass is going to be in which direction? Tell me. Is it going to be in clockwise direction only? And after the impulse, it rotates in clockwise sense, we have assumed. So what I will do, only one torque whose sense is clockwise, so we will take that direction as positive. So what is the torque I will have of that force will be F into x. So the angular impulse is going to be integral of tau dt, just like earlier thing only or not. Torque we can write down as F into x. X is constant. It will come out. It will be integral of F dt. And what we write down for J, if the force F is the one which is causing this impulse J, so J will be equal to integral of F dt. So here F integral of F dt, I can replace it with J. So angular impulse J theta will be equal to x times J. Initial angular momentum about the center of the mass 0. Final angular momentum is going to be equal to ICM omega. In what sense it is? It is in clockwise sense. And we have taken clockwise as positive. So J theta, we write it down as change in angular momentum. And that is x times J, change in angular momentum, final ICM omega, initial 0. So it's going to be ICM omega. And this is going to be, this is our equation number 1. This is our equation number 2. And we can figure out omega, which is going to be xj by ICM. No? And since they're asking us the value of the x such that it rolls without slipping. So in case if it rolls without slipping, then VCM will be equal to R omega. Omega I can write down as VCM by R. So VCM by R will be xj by ICM. And what is our VCM in terms of j? It is j by m. No? So it's going to become j by mr equals to xj by ICM. So JJ will get cancelled. You put the value of the ICM, which is going to be 2 by 5 MR square. So you will find X will be equal to 2 by 5R. All of you understood this thing? All of you understood, no?
Yes, sir.
Okay. Next, suppose if it is two things I'll give you as a homework, all of you try. One thing is, this is a rod which is hinged in the vertical plane about point O. Okay, so it is free to rotate about the point O, and it is a rod, a uniform rod of mass m2 and length L. And here comes a point mass moving perpendicular to the rod, and the mass of this point mass is m1, moving with velocity u0, strikes this rod at a distance x below the point of suspension. So we have done one question where we were applying an impulse. So we can apply an impulse by having two particles undergoing collision also. No? So m1 will be applying a large force on our rod, which is something which is nothing but impulse only. So this point mass is going to come and strike at a distance x below the point of suspension, and the coefficient of restitution is given to us as E. you will not be able to solve it, just you try as a homework. So determine the angular speed of the rod just after the collision. Okay. So one more question I'll give you that I'll discuss in the next class tomorrow. Next is what we have got is there's a rod which is placed on a rod placed on a smooth horizontal surface. Same rod, same mass, everything same. And then what we have is this is the center of the mass of the rod. And there's a point mass which is moving perpendicular to this rod on the same plane in which this rod is kept, of mass m1 moving with velocity u0, strikes this rod at a distance x below the center of the mass as shown in the figure, and coefficient of restitution here also given to us as E. So determine the angular speed and VCM of the rod just after the collision. So in the earlier example that I took in the class, instead of mass coming and striking a rod kept on a smooth surface, I give you the impulse that is applied on the rod. Here, that impulse is going to be caused because of this mass striking the rod. Okay. So try this too as a homework. I can't expect that you'll be able to solve. Just you think what you will do, then I will discuss in the next class. Okay. And one more thing you have to do, apart from this, you try to read this 5.1. This is some extra topic, but still I'll be taking it tomorrow only. After this, some few extra topic also I have to teach. That is something I teach from my side, not like required to teach that thing. So this one I will complete in the next class. So next class, your syllabus will be over. So yeah, I did not took extra classes earlier, so up to take extra classes now. But whatever I have taught till the last Sunday class, now up to that, you will be able to solve RBD questions. So you don't have to worry much. But still, this is there in our syllabus. Okay. I'll share this thing in our Google Classroom.